Lewis dot structures, it's going to be the topic of this lesson, and we're actually going to be drawing molecules in this lesson. We'll start off with an introduction to what's called the Octet Rule, which is really central to kind of our ideology of how we draw these lovely structures, and we'll definitely talk about the 3 exceptions for that Octet Rule, and then we're just going to start drawing structures. We're actually going to draw 9 of them, and they're going to get progressively more difficult and cover a variety of different tricky examples and things of this sort, and every kind of example you're likely to encounter somewhere along the way. This is my high school chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss one, subscribe to the channel, click the bell notification. You'll be notified every time I release a new lesson. All right, so before we can draw these structures, we got to talk about this lovely octet rule, and oct meaning 8. So in this case, an octet rule describes that most atoms end up wanting to have a total of 8 valence electrons around them. So we're focusing on the valence electrons in this chapter. It turns out those are the electrons that are involved in bonding. So in chemical reactions, when bonds are broken and bonds are formed, it is just a restructuring of the valence electrons. This is why they get a special name. We've got valence electrons, which is just the outermost shell, and then any closer shells are all just kind of lumped under core. And again, the reason is this valence is really important is because these are the electrons involved in chemical reactions. These are the electrons that are going to be represented in our Lewis dot structures as well. And so just as a reminder, our alkali metals, the group 1 metals, have 1 valence electron. The alkaline earth metals have 2 valence electrons. Borons column 3 valence electrons. Carbons column 4 valence electrons. Nitrogens column 5. Oxygens column 6. Halogens 7. Noble gases 8 valence electrons. And these noble gases end up with a filled shell. They've got the S's full and the 3 P's full for a total of 8 electrons full. And it turns out that's a stable place to be. And so we say they have a filled octet. And we also say that the rest of these elements are trying to look like that and get a filled octet. So if we start with something like sodium here, so we said that sodium here has 1 valence electron, and the way we represent this, we represent each of these valence electrons with a dot, and you put them in pairs on the 4 different sides. We split this up into 4 sides, top, bottom, left, right, and you put the electrons around there up, 2 by 2 by 2. So, and first give every side 1 before you double them up, but with only 1 here, we just pick a side and put it there. So there's the Lewis structure for sodium. Now, we won't deal with metals too much because most of this chapter will be dealing with molecular compounds, which will be made of non-metals, but we could, just for an individual element, put it up there. So we do the same thing now for chlorine. So chlorine, being a halogen here, has got 7 valence electrons. So all 4 sides get 1 before you start pairing them up as well. And so in this side, we're left with in this case, we're left with 1 side having only 1 electron, but that is the Lewis dot structure for chlorine. Now, if we look at kind of what's behind this octet rule, in this case, the sodium here is like, man, I've got 1 extra electron, and metals tend to lose electrons to end up in a situation where it's the previous shell that's still completely full. And that's what's going to happen to sodium here. He's going to be like, you know what, I'm going to give away my electron. And chlorine's going to be really happy about that. And if you recall, chlorine has a very negative electron affinity, loves to gain electron. In fact, when he gains 1 electron, he's going to look like a noble gas and have a filled octet as well. And so in this case, we get that transfer of electrons. Sodium's now going to have a positive charge. Chlorine will now have picked up that 8th electron and have a negative charge. And so there's this transfer of electrons that leads to the creation of both a cation and an anion, and now there's an attraction between them. We just created an ionic compound here. But again, the idea was that we kind of used to represent this, though, happening was that both of these elements, in an attempt to get a filled octet, underwent this transfer of electrons. And that's generally what happens when you have a metal with a nonmetal. So, but what if we have 2 nonmetals? And so in this case, I'm going to have 2 chlorine atoms, each with 7 valence electrons. And now this chlorine's like, hey, give me your electron. And this chlorine's like, no, give me your electron. And up here, chlorine's like, hey, sodium, give me your electron. And sodium's like, okay. So because sodium, being a metal, has a low ionization energy, it's easy for it to lose an electron. But here we don't have any metals, and so nobody has an easy time losing an electron. And if there's nobody there to lose an electron, then there's going to be no transfer of electrons. And so with 2 nonmetals, the solution is simply to share. They're both going to chip in 1 electron and form a pair of shared electrons. That is what we call a bond. In this case, a covalent bond. And so in this case, we'll draw this out, and there's 2 ways we could draw this. most commonly you're going to see shared electrons represented by a line, and each line represents a bond, and represents two shared electrons. So you could also draw them out still as dots though, and you'll see it represented that way as well. So there's our two shared electrons, either still represented as dots or in this case represented as line. It means the same thing, but you'll definitely see the top version more commonly, but I'm sure at some point though you're likely to encounter both. Now one thing you should know is we have the shared electrons again, which represent a bond, but then we have the unshared electrons, and those are called typically non-bonding electrons. So we have bonding electrons represented by the line here or in the middle here, and then we have non-bonding electrons, sometimes called lone pairs of electrons for those non-bonding ones. So just some terminology here. Cool. So whether we have a metal and a non-metal and a transfer of electrons, attempt to get a filled octet for both atoms, or we share electrons, so because now both of these chlorines can count those shared electrons as part of their filled out outermost shell, filled octet. So 2, 4, 6, 8 for chlorine on the left, good to go. 2, 4, 6, 8 for the chlorine on the right, and he also has a filled octet and is good to go. So when you've got two nonmetals, it's generally a sharing of electrons that leads to getting a filled octet and your covalent bond. Okay, so this is really what's behind this octet rule, but there are three cases where you actually get exceptions of atoms that don't satisfy the octet rule. And so I want to deal with these three cases, and the first is where you've got atoms that go under the octet rule, that aren't actually going to get as many as 8 electrons. And hydrogen is definitely one of them. So if you notice hydrogen, the noble gas he wants to look like is helium. And helium doesn't have 8 electrons in its outermost shell, which is its only shell. It's only got the S, and the S only holds 2 electrons. And so in the case of hydrogen, he only wants 2 electrons, not 8. Cool, now the next exception is going to be beryllium. Now beryllium's fairly metallic, and again in our molecular compounds we're going to be dealing with mostly nonmetals, but there are a couple of exceptions where aluminum or beryllium, even being more metallic, still form covalent bonds. There are exceptions to our rule, and you might see a structure with them, which is why we got to address this. So, but beryllium here has 2 valence electrons, and having 2 valence electrons, beryllium's like, well, I can share one with you, and I can share one with you. And by the time beryllium is done sharing with 2 atoms, he'll end up forming 2 bonds, but he's only going to have a total of 4 electrons around him, not 8. Cool, you'll find out that boron and aluminum do something similar. With 3 valence electrons, they can share with up to 3 different atoms, making 3 bonds. And if they make 3 bonds, they're only going to have 6 electrons around them instead of 8. So these are the 4 elements that routinely go under the octet rule, and you'll encounter hydrogen on a regular basis. The other 3, you may encounter them, you may not. They do show up here and there, but not super common. All right, so that's your first exception to the octet rule. Your next exception to the octet rule is elements that go over the octet rule. And when an element goes past 8 electrons in its outermost shell here, as we'll see, we call that an expanded octet. So, well, if we look at where the octet rule comes from, you've got an s orbital, you've got 3 p orbitals, and the octet rule comes from the idea, again, that to look like a noble gas, you want to fill up that outermost shell, which means filling up your s and your p's. And lo and behold, you've got 8 electrons. So, however, starting in the 3rd shell, you not only have an s subshell and a p subshell, you also have a d subshell. And so as a result, you actually have room for more electrons. So, but only starting in the 3rd shell. First shell only has S. Second shell has S and P, but it's only starting in the 3rd shell that you have S, P, and D. And that's why this next rule deals with elements in the 3rd row of the periodic table or lower. If they want to go over the octet rule, they can tap into those d orbitals and shove some more electrons in there, and they're not limited to just 8. It doesn't mean that the elements from this row and on down have to go over the octet rule, but they have the option to go over the octet rule if the structure demands it. Okay, finally, your 3rd exception to the octet rule deals with when you have an odd number of electrons in your structure. So notice if every atom gets a filled octet, then every one of them is going to be seeing 8 around them. Now some of those will be shared, so it's not like you're going to have a multiple of 8, but every atom has 8 around them. There's no way that you can't have anything other than an even number then of total electrons if they're all seeing 8. So If your overall structure then has an odd number of electrons, then somebody's not going to have 8. It's just the way it's going to work out. And you're going to find out that somebody's going to have 7. And the most common example of this is NO. And it turns out in NO, you take your less electronegative element, nitrogen, and he's only going to end up with 7 instead of 8. And that's what happens when you have an odd number. In fact, I can't think of another example off the top of my head besides NO. And that's generally the way it works. Just make sure you get as close to 8 as you can, and your least electronegative atom, give him 1 short. Okay. So now we've dealt with the octet rule, we've dealt with exceptions, and we've learned how to draw, in this case, Lewis dot structures for individual elements as well as ions, and we even did one molecule without even noticing it. But now we got to formally kind of go through the rules for how we draw Lewis dot structures. We're going to do 9 examples. We're going to start off easy and make them a little harder as we go and hit some notable tricky examples along the way. All right, so when you go to draw a Lewis structure, first thing you should really do is just figure out how many valence electrons you've got. Again, it's just the valence electron that show up in the structure. So in the case of CCl4, so carbon here's got 4 valence electrons, and each of the chlorines has 7 each. 4 times 7 is 28, plus another 4 is 32 valence electrons. So we'll start there. So next thing you want to do is set up what I'm going to call your skeleton of your molecule. And your skeleton of your molecule, you're going to typically choose one atom to go in the center and then connect it to all the outside atoms with a single bond. So it turns out there's going to be single bonds, double bonds, and triple bonds possible, but you're going to start off with your skeleton, all single bonds to start. All right, so how do you decide who goes in the middle? Well, there's 2 ways to look at this. So typically the atom in the middle is the one that has to make the most bonds. And so typically you want to then choose the atom to go in the middle that can make the most bonds. And so if you look at this, the halogens are 1 electron short of looking like a noble gas, and generally they typically make 1 bond. So oxygen's column, they're 2 electrons short from a noble gas and typically end up making 2 bonds. Nitrogen's column is 3 electrons short of a filled octet of a noble gas and typically make 3 bonds. Carbon's column typically makes 4 bonds. Now boron and aluminum, you might recall, are exceptions. Instead of wanting 8, they only want 6 electrons total around them. They start with 3, they're only 3 short of that, so they go back down to 3 bonds. So 1 bond, 2 bonds, 3 bonds, 4 bonds, back to 3 bonds. That is what is typical. And so if you look, generally as you move from right to left, especially because boron and aluminum are not super common, as you move from right to left, you can make more bonds. So, well, if you move from right to left, you're also getting less electronegative. And so often we present the rule and say that put the least electronegative element in the middle, with one glaring exception, except never put hydrogen in the middle. Hydrogen can only make 1 bond max since he's only trying to get 2 electrons. So put the least electronegative element in the middle, but never hydrogen. Exclude hydrogen from that as an option. So in this case, carbon is less electronegative than chlorine, and so carbon's going to go in the middle. And notice carbon typically makes 4 bonds. Chlorines only make 1 each typically, and so we should put carbon in the middle by any way we kind of figure this out. So we'll put carbon in the middle, we'll surround him with 4 chlorines, and we'll connect them all with a single bond. So that's where we start. So we counted up our valence electrons, we've now set up our skeleton. Third thing you want to do is fill up the outer atoms. If they want a filled octet, then give them 8 electrons total. So fill them up with non-bonding electrons. So in this case, I'm just going to start filling up these chlorines on every side. So fill up all the outer electrons. You'll always have enough to fill up those outside atoms, so just fill them up without worrying about counting. So now in some cases you'll have more electrons left over that you'll put on the central atom, in some cases you won't. So this is the first time you actually got to count up your total. And you want to see, out of the 32 electrons you should have in your structure, do you have any left to give the central atom now? Well, in this case, 2, 4, 6, 8, that's 8 there. 8 around this chlorine, 8 around this chlorine, 8 around this chlorine. We've used up 8 times 4. We've used up all 32 electrons. There are none left to give the central atom. Now, since we worry about the outside atoms first and the central atom last, sometimes you end up with the central atom being full and sometimes you don't. And so once you run out of electrons, you have to ask yourself, is that central atom full? I like to say, is the central atom happy? And in this case, is he happy? Is he full? Well, in this case, he's like, I got those 2, those 2, those 2, those 2. That's 8. And he's got a filled octet. And he is happy. And this is your Lewis dot structure for CCl4. Let's move to the next example here, and this is NF3. And again, first thing I want to do is get a total number of valence electrons, and nitrogen here is going to have 5 valence electrons. Each of the fluorines has 7. 3 times 7 is 21, plus 5 is 26. All right. Nitrogen is less electronegative and can make more bonds, and we'll definitely put nitrogen in the middle. What you'll find out is that if your molecular compound is binary, i.e. made of two elements, generally it's the first one listed that'll be less electronegative and generally end up in the middle. So we can kind of look at that as well. So but that's when it's made of two elements. We'll see an example in a little bit where it's made of three, and that's not the case. But we'll put nitrogen in the middle. We'll surround him by 3 fluorines with all single bonds to set up our skeleton. Step 2, step 3, fill up all the outside atoms with non-bonding electrons. And again, you'll always have enough to accomplish this. So you don't even have to count yet. But now they're full, and the question is do you have any leftover electrons for that central atom, for nitrogen in this case? Out of our 26 electrons, we've used up 2, 4, 6, 8 there. 8 around that fluorine, 8 around that fluorine. We've used up a total of 24. Any electrons you've got left over after filling up the outside atoms always end up on the central atom. Well, in this case, I've got 2 electrons left over. And so any electrons that are left over go on the central atom 2 by 2 by 2. You put them on in pairs. And so in this case, I'll put them on as a pair right there. And then we're out of electrons. We've used all 26 at this point. And again, once you run out of electrons, you got to ask yourself, is the central atom happy? Is the central atom full? In this case for nitrogen, 2, 4, 6, 8. And he totally has a filled octet. Notice we said earlier also that we expect nitrogen being 3 electrons short of a filled octet to typically make 3 bonds. And lo and behold, nitrogen is indeed making 3 bonds in this structure, as we might have anticipated. Cool, we'll find out it's not true in every case that an atom will make the typical number of bonds, but we'll also see that it's got some predictive value in the future. But this, again, is your Lewis structure for NF3. All right, next couple examples here. So first is HCN, and once again, we'll total up the valence electrons. So hydrogen's got 1, the carbon's got 4, and nitrogen's got 5, and 1 plus 4 plus 5 is a total of 10 valence electrons that should appear in our structure. So carbon is not the least electronegative, but again, we're not supposed to include hydrogen in that, so carbon out of the 2 left is the less electronegative and will definitely go in the middle. And notice when you've got typically more than 2 atoms, they often give them to you in the order in which they actually occur. So, but we're definitely going to put carbon in the middle regardless of how we determine that. Cool. Next thing we'll do is fill up the outside atoms. And my question for you is, why is this a bad idea? What's wrong with filling up hydrogen like that? Well, once again, if you recall, hydrogen does not want a filled octet. Hydrogen just wants 2 electrons to look like helium. And so it turns out before I drew any of those dots, hydrogen was already full. He did not want any more electrons. So when I say fill up the outside atoms, usually that means fill up their octets, but not for hydrogen. So now we'll fill up the nitrogen though, give him his filled octet. And then we've got to do an accounting. Do we have any electrons left to give the central atom, the carbon in this case? Well, 2, 4, 6, 8, 10, and we've used all 10 of our electrons. None left to give carbon, and once you run out of electrons, you got to ask, is the central atom full? Is the central atom happy? And in this case, he is not happy. He has only got a total of 4 electrons around him. He wants 8. He needs 4 more electrons. And when this occurs, when you run out of electrons and your central atom is not full, then one of the atoms adjacent to him, next to him, has to share some electrons. Well, in this case, hydrogen doesn't have anything to share. It's non-bonding electrons that you can share, and hydrogen doesn't have any. But nitrogen does. And so what nitrogen's going to do, we're going to erase these non-bonding electrons and make them bonding electrons. They were unshared, now they're shared. Carbon's a little closer to being happy, but still only has a total of 6 electrons around him, so nitrogen's going to share again. And this is how we end up with a triple bond. And so it turns out a triple bond is stronger than a double bond, and a double bond is stronger than a single bond, assuming it's between the same atoms. And in this case, this is how you end up with either double or triple bonds. When your central atom is not full, once you run out of electrons, that's when you're going to end up making multiple bonds to that central atom. Cool. But this is your Lewis dot structure for HCN. All right, moving on to CO2. So CO2 is one of the most common examples to show up somewhere along the way. You're going to see it in your class somewhere. I highly recommend that once we figure this out, probably worth your time to even memorize its structure to save yourself a little time somewhere along the way. But carbon's got 4 valence electrons. Each of the oxygens has 6 each. 2 times 6 is 12, plus 4 is going to be a total of 16 valence electrons. In this case, we set up our skeleton. Carbon's less electronegative. Will go in the middle. And there is our skeleton. Once our skeleton's set up, fill up the outer atoms with non-bonding electrons. So we'll fill up these oxygens. And now they're full. And now we've got to take an accounting. Do we have any electrons left to give carbon? Well, 2, 4, 6, 8, 10, 12, 14, 16. Nope, we've used all 16 electrons up. And carbon's definitely not happy. That's my next question. Is carbon happy? No, he's only got a total of 4 electrons around him. He wants 8. So somebody next to him is going to have to share. And now we have a unique situation. For the first time, we now have 2 adjacent atoms that have something to share. And so if we look, carbon's got 4, he wants 8. We're going to have 2 pairs that are shared, a total of 4 electrons that get shared. And it turns out there's actually 3 ways we could do this. We could say, well, you know, it'd be fair if each oxygen got to share a pair. That would be a fair world. That would be nice. So, well, it turns out it's not about being nice and it's not about being fair. So it turns out it's about something else entirely. It's also not about symmetry. So if you're like OCD and thinks it looks better this way because it's symmetrical, it's also not about your OCD. So in this case, we could also have the oxygen on the left do all of the sharing. Share not just one pair, but share a second pair. And that's something we have to consider. We could have also had it been the oxygen on the right that did all the sharing and end up with a triple bond instead. And so when you've got multiple structures that could potentially end up being correct, we refer to this as being an example of resonance. So although most of the time for high school chemistry, we usually like to kind of talk about this word when we've got multiple structures that are all equivalent. In this case, we've got multiple structures, but we'll see these are not all equivalent. We're going to have a way to figure out which of these is the best structure. And again, it's not about fair and not about symmetry. It's going to be about what we call formal charge. So it turns out, based on the number of electrons in the structure around an atom compared to its normal number of valence electrons, we can give it a formal charge. When it has fewer than normal, it'll end up being positive. When it has more than normal, it'll end up being negative. Well, the rule works like this. You want as few atoms to have formal charges as possible. You'd love to have all these have a charge of 0, essentially. Few atoms to have formal charges as possible. You also want the magnitude of those charges to be as close to 0 as possible, like +1 and -1, way better than +2 and -2, things of that sort. So you want fewer formal charges, lower magnitude formal charges, and then if that still doesn't determine the difference, the last thing is if you've got a difference in where a negative formal charge is located, you want to put it on the most electronegative atom. Keep in mind, again, fluorine's the most electronegative atom, then oxygen, and again, the closer you get to fluorine, the more electronegative. So that's how we decide this. So, but it turns out there's a lovely formula for calculating formal charge, and we're going to go through the very formal formula for formal charge, and then we're going to go through an informal method that we'll use in practice. So it turns out your formula says take the normal number of valence electrons for that element. So like for oxygen, that would be 6. Take that normal number of valence electrons and then subtract the sum of the non-bonding electrons. In this case, this oxygen has 1, 2, 3, 4 non-bonding electrons plus half of the bonding electrons. Well, in this case, the oxygen has 1, 2, 3, 4 bonding electrons as well. And so in this case, 4 plus half of 4, which is 4 plus 2 is 6, and 6 minus 6 would give us a value of 0. That's how the formula works. So, but your likelihood of remembering that formula without spending a little time on it, not so great. However, you can really shorten it down to take the normal number of valence electrons, and instead of like something in brackets here that you got to remember, it's the sum of the dots and lines around that atom is the way I like to think about it. You think about it in this case that you don't even look at these as all being representing electrons. You just look at these as 4 dots and these as 2 lines. And you say there's 4 dots and 2 lines. And so the sum of the dots and lines would be 4 plus 2. And then 6 minus the sum of the dots and lines, 6 minus 6 would be 0 in this case. And that's the way I'm going to look at it. So normally I'd go for oxygen at 6 minus 1, 2, 3, 4, 5, 6, and that's 0. That's how I usually look at this. So much better working definition that we can use in practice. All right, for carbon, it would be 4 as his normal valence, and 4 minus 1, 2, 3, 4 lines, no dots, is 0 as well. And finally, for the oxygen on the far right, 6 minus 1, 2, 3, 4, 5, 6, also 0. None of these have a formal charge in this structure. That makes it very good. Again, we want as few atoms to have formal charges as possible. Okay, one other thing to note. So it turns out, easy way to kind of anticipate when we should expect a formal charge. If an atom is making something other than its normal or typical number of bonds, usually is going to end up with a formal charge. So in the case of oxygen, we usually expect oxygen to be making 2 bonds. 2 electrons short of a filled octet usually makes 2 bonds. Well, this oxygen was making 2 bonds, and lo and behold, it had no formal charge. They go hand in hand. Whereas in this next structure, I see that this oxygen's making 3 bonds. I should expect him to probably have a formal charge. This oxygen's only making 1 bond. I should expect him to probably have a formal charge. Whereas carbon, on the other case, again being 4 electrons short of a filled octet, typically makes 4 bonds. And this carbon is making 4 bonds, and I'm probably going to anticipate that he's not going to have any formal charge. And that's exactly how it's going to work out. Again, so for oxygen, normal valence is 6, and 6 minus 1, 2, 3, 4, 5. So 2 dots, 3 lines. So 6 minus 1, 2, 3, 4, 5 is plus 1. You draw it next to it there, and for the other oxygen on the other side, 6 minus 6 dots in 1 line. So 6 minus 1, 2, 3, 4, 5, 6, 7 is negative 1. And then for the carbon in the middle, his normal valence is 4, and 4 minus 1, 2, 3, 4 is 0. And now we can see the actual comparison we should make in between these first 2 structures of why the first one is definitely superior. Again, it wasn't about it being symmetrical or anything of that sort. It was as all the atoms have no formal charges in this one, 2 of the atoms have a formal charge in the next one. And so we'll find out that this is the best structure for CO2. So it turns out that this last one here would just have the exact opposite here. You'd actually end up with a positive formal charge now with the oxygen on the right, negative formal charge with the oxygen on the left, no formal charge on the carbon, and once again, just goes and shows us that the top would be the best Lewis structure. So if you were asked to provide the best Lewis structure for CO2, you're definitely providing the top one, not these bottom 2. Cool, so that's the relevance of formal charge. And it turns out all of the structures we've looked at up to this point, all the atoms were making their normal, typical number of bonds, and there were no formal charges to worry about. But being that this is how we distinguish between these resonance structures to figure out which is best, that I figured was the best time to bring it up. All right, so the next example here is N2O. And if I want to ask you as tricky a question as I can probably ask you involving Lewis structures, it's going to be N2O. And it turns out N2O is going to be doubly tricky, as we'll see. And so first thing, again, we'll treat it just like normal, though. As long as we follow the rules and apply them appropriately, we should still get the right structure. So first rule, again, let's just add up our valence electrons, get those on the table at least. And nitrogen's each got 5. 2 times 5 is 10. Oxygen's got 6, so 10 plus 6 is 16. Cool, and then we set up our skeleton, and the big mistake students often make here, first place is tricky, since there's 2 nitrogens, only 1 oxygen, they typically want to put the oxygen in the middle, because that's normally the way it works out. The one you have 1 of goes in the middle, and the others go on the outside, but again, doesn't work that way. The atom that goes in the middle is the one that can make more bonds, which is generally the less electronegative one. Well, nitrogen's less electronegative than oxygen, and generally makes more bonds, 3 instead of 2. And in this case, it is one of the nitrogens that actually is going to go in the middle. That's our central atom. You put the oxygen in the middle, you're not going to come out with the right structure. So that's the first tricky part, but we got more trickiness coming, as we'll see. But once we've got our skeleton set up, we'll fill up the outside atoms with non-bonding electrons. Cool, and once they're full, we have to take an accounting, and we've got 8 electrons used over here and 8 more over here for a total of 16. There are no electrons left. And the question we have to ask ourselves is the central atom happy? In this case, this nitrogen is not happy. He's only got 4 electrons around him, not 8. He needs 4 more, so he needs the atoms around him to do some sharing, in this case, 2 additional bonds. And the question we have to ask ourselves is, well, who's going to do the sharing? Instead of having 2 identical atoms as options, we actually have 2 different atoms this time, and that's going to add some complication to this. So we really, once again, end up with 3 options. We could say, well, let's just make it equitable and fair and symmetrical and have both do the sharing. So this nitrogen could share a lone pair, and this oxygen could share a lone pair, and we get a double bond on each side. That's one option. We could have either the nitrogen on the left or the oxygen on the right do all the sharing. So if I had this nitrogen share the first pair and also the second pair do all the sharing, I could end up with this structure. And then finally, if I had the oxygen doing all the sharing, so it could share the first pair and then share a second pair, and I could end up with this structure. And so these are our 3 possible resonance structures. And the question is, well, how do I determine which is the best structure for N2O? And again, it's not about symmetry, it's about formal charge. And if we kind of go through this, we're just going to assign formal charges here. So for nitrogen, normal valence is 5. And so 5 minus 1, 2, 3, 4, 5, 6 is negative 1. 5 minus 1, 2, 3, 4 is plus 1. And I find it easiest if I just do all the nitrogens at the same time. 5 minus 1, 2, 3, 4, 5, 0. 5 minus 1, 2, 3, 4, plus 1. 5 minus 1, 2, 3, 4, 5, 6, 7. That's horrible. Minus 2. 5 minus 1, 2, 3, 4, plus 1. And then we'll do the oxygens. Oxygen's normal valence is 6. So 6 minus 1, 2, 3, 4, 5, 6, neutral. 6 minus 1, 2, 3, 4, 5, 6, 7, negative 1. And 6 minus 1, 2, 3, 4, 5, plus 1. So now we see, in contrast to what we saw with CO2, there's no structure where there's no formal charges. That's off the table. So we want the fewest formal charges, fewest atoms to have formal charges. Well, these each have 2 atoms with formal charges. This one has 3. He's out. Not him. We also want those formal charges to be closer to 0. So plus 1 is better than plus 2, minus 1 is better than minus 2. He'd be out again. But I still got no difference between these two. Each of them only have 2 formal charges, and it's a plus 1 and a minus 1 in both cases. And this comes all the way down to that third rule for formal charges. And if you have the choice, you'd prefer the negative charge to be on the more electronegative atom. And so if you notice, the positive charge isn't the difference. It's on the central nitrogen in both cases, but it's the negative formal charge. Would I rather have it on nitrogen or oxygen? Well, oxygen's more electronegative than nitrogen, and so I'd prefer it be on the oxygen. And that's why the middle one here, not the symmetrical one, is our best resonance structure for N2O. This is your best Lewis structure. And it all came down to formal charge. If you're OCD and it's all about symmetry, you're going to get this one wrong. And that's what makes it doubly tricky. So again, you had to first realize that it was a nitrogen that went in the middle, not an oxygen. And then realize that, again, it's not about symmetry. It really comes down to the best formal charges in choosing your best resonance contributor. So let's move on and talk about SF4. And in this case, this is going to be a first example of what we call an expanded octet, where we go over the octet rule. And I don't expect you to realize that from the get-go, but as we apply the rules, we'll find out it's just going to happen. And it's going to happen for sulfur. But once again, sulfur is in the third row of the periodic table, and again, third row or lower, you are allowed to go over the octet rule and have an expanded octet. It doesn't mean that every structure you'll have one, but it just means that if you do end up that way in a structure, it's totally allowed, third row and lower. So in this case, sulfur's got 6 valence electrons. Each of the fluorines has got 7. 4 times 7 is 28, plus 6 is 34. So we got 34 valence electrons to deal with. And in this case, sulfur's less electronegative, and we'll put him in the middle. All right, and from here, we'll fill up those outside atoms. Skeleton's good to go. And again, you'll always have enough to fill them up, so you just kind of fill them up blindly. No need to count just yet. But once they are full, now you need to take an accounting. And in this case, I've used 8 around every single one of the fluorines. So that's 8 times 4 is 32, and I have 2 electrons left. And anytime you've got electrons left after filling up the outside atoms, it always goes on the central atom. And you're going to put them on the central atom pair by pair. And so in this case, you're like, well, where do I put them? It's already kind of full. It's all 4 sides are full. Well, then you put them on the diagonal. And you don't put them on like one each on 2 separate diagonals. You're going to put them on 2 by 2 in pairs. So you're just going to pick one of these diagonals and put the last 2 electrons as a pair right there. Cool. And then you have to ask yourself, is the central atom happy? Is he full? Well, in this case, he's more than full. He's got 10 electrons around him. He's drunk with electrons. He's more than happy. But that's okay. Again, sulfur, again, being in the third row or lower, he's allowed to go over the octet rule. And this is your Lewis structure for SF4, our first example of an expanded octet. All right, so these next 2 examples, it turns out, are also going to end up having an expanded octet. But again, it's not something I expect you to predict, but something that if we just appropriately follow the rules, it'll just happen. In this case, iodine and chlorine are both halogens and have 7 electrons each. So 4 atoms with 7 valence electrons should get us to 28 in this case. Iodine's less electronegative, and so we'll put him in the middle. Cool. Got our skeleton set up, and we will fill up those outer chlorine atoms. And now we've got to take an accounting. How many electrons do we have left? Do we have any left to give to iodine? Well, again, 2, 4, 6, 8. There's 8 around each of the 3 chlorines. We've used up 24. We've got 28. So there's 4 electrons left. And again, once you fill up those outer atoms, any additional electrons always go on the central atom. And in this case, again, they go on pair by pair. So I've got 4 electrons left, so I've got to put 2 pairs on here. And so instead of putting like one across the top, we usually kind of split this up into 2 diagonals up there. So, but technically you can put it one over, one up here and one on a diagonal over here, and it's technically the same thing. This is just usually what you're going to see. And in this case, you got to ask yourself, is the central atom happy? And once again, he is more than happy. He's got 2, 4, 6, 8, 10 electrons around him. He's gone over the octet rule. But again, iodine, definitely third row or lower in this case, and definitely allowed to go over the octet rule. All right, this next example is kind of unique because we actually have a noble gas in here. The noble gases make very few compounds because they already start off with a filled octet. But when they do, the noble gas atom is always the central atom. Now, it turns out the smallest noble gases don't form any compounds. It's just the bigger ones like xenon that do, and it turns out typically in combination with very electronegative atoms, as we got the case here with fluorine. So in this case, xenon's got 8 valence electrons. Each of the fluorines got 7. 4 times 7 is 28, plus another 8 is 36. And once again, with a noble gas always goes as the central atom, always goes in the middle when it's in a compound. The very few examples that we have. So there's my skeleton, noble gas in the center. Fill up the outside atoms just like normal. And then we got to do an accounting. Do we have any electrons left over? And in this case, we've used 8 around every one of the fluorines. So 8, 16, 24, 32. And we've got 4 electrons left. And once again, we're going to put 2 lone pairs on the xenon, on the central atom. And typically we put them on opposite diagonals. Although if you put them on 2 adjacent ones, it's not technically wrong, just not usually how you'll see it represented. And you got to ask yourself, is the central atom happy? And once again, he's over the octet rule. But if xenon's going to make any bonds, he had to be over the octet rule because he started out with a filled octet. And so in this case, he's got 2, 4, 6, 8, 10, 12 electrons around him, which again is okay. Xenon is definitely third row or lower, definitely allowed to go over the octet rule. All right, so our last example is going to be unique for 2 reasons. So one, this is the first example of an ion we've done. And when you've got an ion, it's either a cation or an anion. And when you've got an anion with a negative charge, you have to add electrons. If it's -1, add 1 extra electron to your total. If it's -2, add 2 extra electrons. And then in contrast, if you have a cation, you have to remove electrons. +1, remove 1 electron from your total. +2, remove 2 electrons, so on and so forth. So other thing that's unique is when you draw the Lewis structure for an ion, you're always going to draw it in brackets and then put the charge in the upper right-hand corner, right on the other side of the bracket. So with a -1 ion, we'd put this in brackets. Now it turns out there's 2 reasons you end up using brackets when drawing Lewis structures. One is for ions, and the other is when you have multiple equivalent resonance structures. Now, we've alluded to resonance structures up till now, but I haven't really talked much about it because I wanted to save it for this discussion right here. Because not only are we going to have multiple structures that are possible, but they're all going to be equivalent. And when that's the case, you've got to draw them all, and you also put them all in brackets. Even if it's not charged, you still put multiple resonance structures in brackets. So 2 reasons to use brackets that turn out both apply to this one. But whether there was resonance or not, because he's charged, you'd have brackets. Or if there was resonance and even without a charge, you'd still use brackets. But in this case, we're going to use brackets for both reasons. All right. So if we look here, nitrogen's got 5 valence electrons, and each of the oxygens is 6. 3 times 6 is 18, plus 5 is 23. And because we're -1, we add 1 extra for a total of 24 valence electrons. Nitrogen is less electronegative, and so nitrogen's going to go in the middle. So there's our skeleton. We'll fill up those outside atoms, just like normal. And once we fill up the outside atoms, we've got to say, are there any electrons left over to give to the central nitrogen in this case? Well, there's 8, 16, 24, and we are out of electrons. Once you're out of electrons, you ask, is the central atom happy? Is our central atom happy? Is he full? No. 2, 4, 6. He is 2 electrons short from a filled octet. And so somebody next to him is going to have to share. Well, in this case, we not only have just 2 atoms that can share, we actually have 3 adjacent atoms that all have lone pairs of electrons they could share. And in this case, what's even more is they're all the same exact atom in the exact same situation. And so the truth is then, we're going to end up with 3 different possible structures we could draw. We got to have the oxygen on the left share, the oxygen on the bottom share, or the oxygen on the right share. And as a result, we're going to end up drawing 3 different structures here. So I'm going to set up my skeleton 3 times over. To set up drawing these 3 different structures. Okay, so in the first example, I'm going to have the oxygen on the left do the sharing. So I'm going to erase one of his lone pairs and make them shared electrons, bonding electrons instead, and got a double bond there. In the next one, I'll have it be the oxygen on the bottom doing the sharing instead. So we'll erase one of his lone pairs, make a double bond there. And in the last one, I'll have it be the oxygen on the right that's doing the sharing instead. And so we get these 3 structures. And it turns out, how do we distinguish between resonance structures? It comes down to formal charge. But you can kind of anticipate that these should all be equivalent, because in every case, you've got one oxygen with a double bond and then 2 with a single bond in every single case. And so in principle, the formal charges should work out, at least in some, the same, just in different locations. So let's take a look here. So for the oxygen on the left, so 6 minus 1, 2, 3, 4, 5, 6, he's neutral. So is that one that's double bonded? So is that one that's double bonded. But these guys, making something other than the normal number of bonds, we should expect to have a formal charge. And 6 minus 1, 2, 3, 4, 5, 6, 7 is -1. Same thing with this oxygen, in fact, for all the single bonded oxygens. Cool, nitrogen also is making 4 bonds instead of 3, so his normal number, so we should expect a formal charge there as well. And again, nitrogen's normal valence is 5, and 5 minus 1, 2, 3, 4, plus 1. And so we see these are all equivalent. The nitrogen's got a +1 formal charge in every structure, and 2 out of 3 oxygens got a -1 formal charge. And so as a result, our rules for distinguishing between resonance structures based on formal charges don't help us. These are all exactly equivalent. And when that's the case, you actually have to draw all 3. So unfortunately, you can't just say one's best. So you've got to draw all 3. And when you've got these multiple equivalent resonance structures, you got to do 2 things. Once again, we put them all in big set of brackets, and if it's got a charge, you add that up in the upper right-hand corner. And then you also put a little double-headed arrow in between each of the structures. And be careful, there's a couple different double-headed arrows we draw in chemistry. One of them you'll learn to draw in the second half of this course will look like this. And that means something different than this double-headed arrow right here. So make sure you're doing the appropriate double-headed arrow here. This is the double-headed resonance arrow. And that's there to trick you. So, because we got to talk about what these resonance structures really mean. Because if we look at this, it looks like we have 1 double bond and 2 single bonds. Well, it turns out a double bond is stronger than a single bond, just like a triple bond would be stronger than a double bond between the same 2 atoms. And so what this looks like is that we have 1 stronger bond and 2 weaker bonds in this particular structure. And it turns out a stronger bond ends up being a shorter bond. The atoms are pulled closer together. And so it looks like we have 1 shorter bond and 2 longer bonds. Problem is that when we actually look at this lovely structure, all the bonds are exactly the same length all the time. And it's just like, well, that's weird, because I draw my structures and I even connect them with this lovely arrow, and we use the word resonance. And that word resonance makes me think of the word resonating. And I'm thinking, oh yeah, these are just resonating back and forth as indicated by that lovely arrow. Totally false. Far from the truth. We're just trying to trick you. So these are not resonating back and forth. It's not like you took a picture of this, at one instant it looks like this, and then you take a picture 1 second later and now it looks like this, and then 1 second later now it looks like this. Not true at all. This lovely ion never looks exactly like this or this or this. We're drawing these resonance structures as a tool to figure out what the real structure of this ion actually is. And it turns out the real structure is an average of all these. And so if we take a look at what that average actually looks like here, well, we have at least 1 bond to all the oxygens, but in this structure, the oxygen is double bond, but in this too, it's a single bond. So it actually has a little more of a bond, a partial bond. Same thing with this one, and same thing with this one. And we draw those partial bonds as a dashed line. So it's not a single bond, but it's not a double bond either. It's some one and something of a bond. In fact, we can calculate what fraction of a bond it is because there's 1, 2, 3, 4 bonds between the oxygens in 3 different locations. And so 4 bonds spread out over 3 locations means it's a 4/3 of a bond, 1 1/3 bond. So every one of these bonds is 1 1/3 of a bond all the time. So again, you never have any of these bonds any different in length or any different in strength. So, and this is a weird thing because you actually got these 2 electrons that in this structure we drew those extra 2 electrons that are bonding right here. In this structure we drew them here, and in this structure we drew them here. But what we see the truth is that those 2 extra electrons are actually shared in all 3 locations all the time. That's weird. Like if I told you, yeah, right now I'm teaching, you guys on camera here in Tempe, Arizona, but I'm also in South America teaching a physics class, and I'm in Seoul, Korea teaching a calculus class. You'd just be like, okay, time to look for a new YouTube channel, right? So cool, I can't be in multiple locations at the same time, but that's not true about electrons. Electrons actually can be in more than one location at the same time. And when you have resonance, that's the case. And we call electrons that are in more than one location at the same time delocalized. And so when you've got resonance occurring and you draw multiple resonance structures, what it really means is that you've got delocalized electrons, electrons in multiple bonding locations at the same time. Cool. Sweet. So I want to make sure you realize what resonance actually means. Again, these structures don't actually exist. They're just a tool for us to figure out what the real structure actually looks like. One other thing to note, we had a positive formal charge on the central nitrate in every single structure. So we can definitely give him a positive formal charge here. But for the oxygens, in one structure, every oxygen gets a chance to be neutral. But in the other 2, it's going to be negative. And so the truth is, what's the average between 0, -1, and -1? Well, it's going to be a fraction. And so to show that it's some fraction and not a full negative charge, we end up writing this lovely symbol right here. In this case, it actually works out that you could figure out it's a -2/3 of a charge. So, but we don't ever actually get so specific as to define it like that. We use what this letter delta, that's the Greek lowercase d, if you will, the letter delta. And it means partial. We might use it in a calculus class to describe like partial derivatives. So, and in this case, we use it to mean a partial charge. It means it's not a full -1 charge, it's some fraction of a -1 charge. And all 3 oxygens have that partial negative charge that we're drawing on this lovely, again, resonance hybrid, the average of all our lovely resonance structures. Cool, and that was the last one. I highly recommend you spend a little time drawing a bunch of Lewis structures, keep the rules handy, and hopefully over time you will look back at those rules less and less until you've mastered drawing Lewis structures. Now, if you found this lesson helpful, would you consider giving me a like and a share? A couple of the best things you can really do to help support the channel. And if you're looking for the study guide that goes with this, or if you're looking for practice problems, whether it be quizzes or chapter tests, check out my premium course at chadsprep.com.